This is an interesting problem here. We need to find the value of this definite integral from 0 to 3 of the function x times f of x squared dx when the integral from 0 to 9 of the fx dx is equal to 4. So somehow we must transform this function in such a way, find the definite integral, or express this given that definite integral in such a way that we only have fx dx in it, right? And we get rid of the x and we get rid of the x squared as the input of the f and instead have the x. So how do we do that? First, what you want to do, you want to let gx equal to the input of this function f, x squared. And then what you want to do, you want to take the antiderivative of this g function. So the derivative of this g function. As a result, this is equal to 2x. Okay. So now what happens is then this function x times f of x squared dx can be written in this following way. So we have the x and we have the f of x squared dx. Now notice that we can actually use what we have here, and if we do the proper substitution, we can express this whole thing using these two components. So what I'm saying is we can express g prime of x as 2x, but there's no 2 there, right? So to get rid of, if you put g prime of x instead of x here, you will have to account for that 2 that wasn't there before. So what you want to do, you want to bring that 1/2, which will take care of that 2 being there that wasn't there before, right? So now you can safely write this as 1/2 g prime of x. So g prime of x, and now here you want to write f of x squared dx. So the dx will be there, but the f of x squared, you simply plug in the gx inside the input of the f. So you're going to write this as f of g of x dx. As you can see, this is a composition function that you see here. So now what happens is, notice that you can rewrite the order. You can make this look like 1/2 f of g of x, right, the composite function, times the g prime of x dx, right? So I simply just switched the order. I wrote f of g of x, and then I wrote the g prime of x after that. So now, look what's going to happen. Notice that this, if you basically think of this as a chain rule derivative, so if you think of this derivative as a chain rule result of something else, then you can think of the antiderivative. Think of this as being the derivative of something existing before that. And what's going to be that is going to be the antiderivative, capital F of g of x, evaluated from 0 to 3. And why is that true? Notice that this is a composite function, and the derivative that we've derived is the capital F of g of x. If you take the derivative of this, you will first have to use the chain rule, right? Because you would have to take the derivative of the f function, which would give you this, okay, right, the small f of g. But then you would have to also take the inner derivative, right, using the chain rule, because that's the inner function, which would give you g prime of x. So as you can see, what happens is this is the derivative function of this. So if you think backwards, you can think of this as the derivative. Thus, this is the antiderivative, right? This is the antiderivative of this function. And 1/2 is a constant, that's why it stays the same. So we know we can evaluate it from 0 to 3. Now, here's the thing. If we use the first fundamental theorem of calculus, we can express it as 1/2 of f of g of 3 minus the f of g of 0, right? The upper limit, subtract the lower limit from the upper limit, right? When you evaluate the antiderivative function that you've derived. So this is true. Now, since this is true, why not express this as the original integral, right? Because if we know that this is the antiderivative function f, we can treat this g of 3 and g of 0 as the upper and lower limits of the integration instead of 0 and 3. So what I mean is we can write this as 1/2 the integral, the lower limit of which g of 0, and this is g of 3, right? But also, since we're talking about this being the antiderivative, remember that inside you will have a derivative. And what is the derivative of the capital F? It's the small f. It's the small f, right? It's just the f of x dx. Now, why is it not g? Because we already have the g of x being on the top, right? G of 3 and g of 0, right? These are the x limits that we have. G of 0 and g of 3. Right? So this is a powerful trick that we've used. And now look what happens. This is what exactly we wanted to achieve, right? Because we wanted the integrand to be expressed as an f of x and not anything else, not f of x squared, right? Not x times f of x. We wanted to arrive at this conclusion so that we could use this part, because this is a very nice part that now we can use, because here it tells us what the f of x of dx from 0 to 9 is going to be. It's going to be 4. Now you might say, but wait a second, how do we know what g of 3 and g of 0 is? Well, here's the thing. You have the g function here available, right? So the g of x is equal to x squared, right? So we can evaluate g of 0 and g of 3. So now let's see. So what is going to be the g of 0? G of 0 is going to be 0 squared, which is 0. What is going to be g of 3? G of 3 is going to be 3 squared, which is 9. So there you go. You found the limits of integration. So 1/2 from 0 to 9 of fx dx. Okay? So now look what happens. Now you know 1/2 times what? You know this whole thing, this part here, is exactly what we have in the top. This and the derivative written after the constant is equal to 4, right? So the result is 1/2 times 4, which is equal to 4 divided by 2, which is 2, right? So this is the resulting value of the original definite integral that we were so cautiously trying to solve. And we did it successfully by using very nice tricks, using the first fundamental theorem of calculus, the chain rule, undoing the chain rule and going backwards, finding the antiderivatives, understanding the capital versus small letters, etc. So I hope this was useful. Thank you so much for watching. See you in the next video.